All right. So homework. Write a program, creates 100 elements array and fills it with random integers. To display the unsorted array, and then it should sort them. Okay, so we'll incorporate a couple of the things that we started talking about into this, even if you didn't do it in your code, stuff that we were talking about at the end of class last time. So we want to first create a array with 100 elements in it and fill it up with random numbers. Is that the go-to move for this? All right, so we're going to need our random number dealy flippy stuff. And we still have some of that in here. Okay, here's our SRAM thing. So I'll just steal some of this. All right, so that's our thing to give us a random number. We seed the random number generator initially. So now we want to go ahead, and I'm just going to dump this stuff here. We'll go ahead and create our array capable of holding 100 things. So we're going to say int AR array 100, like that. Okay, now remind me, why don't I have to use malloc in here? We talked about malloc versus this syntax last time. Why am I okay using this syntax in here, even if I'm going to pass this to other functions? Go ahead.
I was going to say, because you don't need to pass it to a function outside of main. But...
Well, what if I do? Why am I okay?
Oh,
yeah, so ultimately it comes down to who owned that memory. So when it was created here, that the scope of that variable is to main. So that memory only disappears once main dies. And when main dies, your program's over, right? All programs begin and end with main. All right, so since I define this memory here in main, even if I pass it around to other functions, when that function ends, this guy still exists. Make sense? All right, because that's where the memory was initially created, as opposed to what we did last class, where I would maybe have a function like we had one called create array or something like that, that generated the array and then returned it, but that memory had disappeared at the end of that function. So what we received back in main was a pointer to nothing because the memory was reclaimed by the operating system. Now, having said that, you could still use malloc here and just say, hey, it looks cooler. People think I'm smart, blah, blah, blah. And I might even say, you should do that. You know, similar to the whole curly brace argument where, you know, you're never wrong doing that. So you won't run into things, or even the plus plus operator. You know, if you want to add 3 to something, just say A equals A plus 3. You know, don't do A plus plus, A plus plus, A plus plus, or something like that. Or, you know, maybe initially you do A plus 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 plus, so something like that, and you realize that didn't work. So there's logic to all these things, why things behave a certain way. But at the end of the day, if you just, I just want to make sure I have my speakers on in case there's a question or something online. You want to make sure that you know, you have access to that memory, and if you don't want to have to memorize all this stuff or go back and reinvent the wheel, just do it the way that you know works all the time. Go ahead.
So, why is that so if you declare variable inside of them, so say integer x, and then you have a function inside of main that comes right after that, and below define the function and it includes x. How can x x is in the scope? Inside of the function and
okay, so what he's saying is, let me just give an example here. So I created this variable AR inside of main, right? And now I'm going to create a function called fill array. You know, why doesn't this guy have access to AR?
Yeah.
That's the question you're asking, right? Okay, so variables resolve their most local definition. All right. Now, when we are inside of this scope right here, we don't have the ability to get to main. It's like in a different planet. If we had done this, well, no, okay, so are you saying right after if I call fill array? Yeah, well, so this is me calling the function that I'm writing. There's no way I'm not injecting this variable into this function. I'm just calling, I'm transferring control of my program over to this other place, fill array. So it's like we traveled to another planet to this guy. And when we try to access a variable AR, we're just going to look around on the ground here at this planet and not find anything to find that. We're going to look in the parameter list and say, oh, did they pack it into the space shuttle when they called this thing? They didn't. He doesn't have access to the stuff that's back here on Earth. Okay, so you can think of this as like the home planet where we first started the thing. Things that were local here, I don't have access to there. Now, if I take that variable, and I'm not suggesting you do this, but if you take that and you move it outside of main, now you've made it a global variable that's accessible anywhere inside of this file. Pass it in. Yep. We're really, let's call it 99.9% of the time, the correct solution is to pass it in. Yeah, global is typically considered to be a bad idea. Okay, but these are good questions because scope is a really important thing. And I mentioned a minute ago this idea that variables resolve to their most local definition. So the real question here is, continuing on with this this question is, where am I allowed to look if I'm inside of this function? What are my options for where I can go, searching for that variable? If I'm inside a function, the only place I can search is inside that function, the parameter list of that function, or the global scope outside of main. Okay, because that's just kind of fluttering out in the universe by my space example here. Okay. Those are the only places I'm allowed to look. I don't have access to main, even though I got here from main. I can't go back there until this guy ends. All right. So when I come in here and I say, I try to use a variable AR, it's going to give me the error that says, hey, I've never heard of this dude. Why? Because I don't see you defining it here. I don't see you passing it as a parameter, and I don't see it defined up here in the main scope, which would usually be considered a bad idea to put stuff in a global scope. Okay. Main is not accessible. It's not one of the places I can search. All right. So with my fill array here, I'm going to go ahead and I'm going to pass in for right now an int pointer to that guy. Because ultimately I'm taking this one step at a time. I'm going to have a function that fills my array up with random numbers. So I'll go ahead and pass it the memory address. All right. We've already seeded our random number generator. This guy will take in an int pointer as a parameter. So now he knows about this variable AR because it was passed in as a parameter. So he knows about that dude. He doesn't know very much about that dude. So for instance, this guy's job is to fill up that array. So we want to go through every bucket of that array. So for int I is equal to 0, I is less than what? How many elements are in AR? If your entire world lives right here, how many elements are in AR? We know we created AR with 100 elements up here. But that information is not being passed along, right? So really, the answer is we don't know, right? We can pretend to know. We can say, well, because I'm the one writing this program, I just happen to know that I put 100 elements in there and everything is all fine and good. Pretty bad programming practice to do that. Technically would work in this case since I'm the one who defined the variable and I'm the one who's calling this, but this isn't a very generic function at that point. It only works for 100 bucket arrays. Go ahead.
What does it do if you put more than you defined it as? fill it up for more than 100.
Okay, well, so it depends on the behavior of an older compiler. So as soon as you walk off the end of it, if I have 100 buckets that I've gotten from the operating system and I try to access bucket 102, 104, 108, well, at that point I'm building on land that I don't own. All right. So depending on the vintage of the C++ runtime we're using, it may a common historical mistake is something called a segmentation fault. You get where it's just basically a segmentation fault whenever you see that error says you're using memory that you don't own or that doesn't exist anymore. Okay. Accessing memory that is bad. All right. Another thing it might do is just let you do it. You know, a modern language like Java, C# would not let you do it. It would give you in Java, it's an array index out of bounds exception. It would give you saying, hey, you left your land. That's not your land. You stop doing stuff over there. There are older versions of the C and C++ runtime that would just let you do that. And that's kind of the danger of that programming language is that you can just go, traipsing all over memory, doing whatever you want. So that makes sense. Yeah. So any way you cut it from a programmer's perspective, it would be bad to walk into memory that you don't own. Okay, because it has not been earmarked for you and it might be given to somebody else later on. They might overwrite your data, or I think I used the example, whether it was last class or the one before that long time ago, before they had operating systems where programs ran in their own little protected memory space, you could crash your computer. And then in order to keep doing your homework, you had to reboot your machine because the machine would crash because you just overwrote part of the operating system that was loaded into memory. So you don't want to do that. All right, so let's go ahead and fill this guy up like this first, and then we'll upgrade our approach. Okay. And like I said, I'm kind of merging the solution to the homework with where we were going from last class. So we're still making our progress forward. All right, so I'm going to say AR at bucket I. Notice I've just hard coded the 100 here for right now because I know that's right, just for the moment. Okay. I know that's the right number because I wrote the variable up top. And we're going to say, what is it? Just rand like that. And if you want to have it maybe friendlier numbers, maybe we do like rand mod 100 or something like that. That'll give me 0 to 99. Or here, if I do 101, it'll give me 0 to 100. Yeah, that just gives me friendlier integers to deal with here rather than having a wall of humongous values. All right, so that'll go ahead and fill that guy up with stuff. And then if I want to go ahead, I already have a print array. All right, and I'm just gonna modify that dude to 100 as well. I'm just doing some hard coding for the moment. We're going to upgrade this in a second. So now I have a function called print array that takes in an int pointer, and it just spins through and displays each element of that array with a space between them to the screen. All right, so what's happening right now is, let me go ahead and just call print array out here. You want to prove our point. So I define the array in main. So the memory is created inside of main. Then I'm passing a pointer to that memory to this function called fill array. And I'm basically saying, fill array, your job is to fill this dude up. That's what your whole existence is for. So what does fill array do? It takes this array, it somehow makes a really great guess of how many buckets are in there of 100. We're going to fix that soon. Okay. And it just goes through and puts a value between 0 and 100 inside of each element of that array. And that's it. That's all it does. And it's not returning a value or anything. This guy is void. So then at the end of this function ends. He's done doing his job, right? We haven't returned anything. We haven't done anything. But since I passed in a memory address, any changes I made to that have side effect. All right. So I changed crap up in real memory. All right. So now control is transferred back here to main. So this line is now done. Then I pass that memory address into print array, another function. What does print array say it should do? Print array takes in, an integer pointer, and it goes through again. I've made a really good guess. Okay, I'm batting 1,000 here. Just there's 100 things in there. Okay, and it's going to go through and just display them. All right. So there is my random values. Okay. Now, one thing we saw here is evidence of what we talked about a few minutes ago with the scoping rule thing. Who owned AR? AR was invented, born here inside of Maine. So Maine owns that memory, and that memory doesn't go away until Maine goes away. All right. So at this point, Maine doesn't go away until after I've called this and after I've called this. So I'm safe passing in this pointer to fill array, and he just goes and throws a bunch of stuff into that memory location. And when he's done, that stuff still existed in that memory location because Maine is still alive. The pointer hasn't been given back. All right. Then I pass along the same memory address to print array and say, hey, I've already loaded this thing up. Go ahead and display it. Okay. And again, he's doing the same thing. If I forget to fill array, I'm probably going to get a bunch of zeros here because that's the default value. Oh, we get whatever values are currently sitting in those memory locations, which is fun. Is it truly random? I don't, it's possible. At the very least, these numbers cannot be trusted for anything. We didn't put them there. These are the values that were located at those memory addresses. This does tell us one thing though. It says that when we request enough memory to hold 100 integers, it did not go through and initialize those memory addresses to default values. It didn't go through and fill it up with zeros or anything. It just says, look, this is your land. You know, you want to bring bulldozers in and clear what's already there, you feel free. But right now, whatever's on that land's on that land. All right. And that's what we're seeing here, which from our perspective, this is useless stuff, right? We don't want to rely on this. Go ahead.
If you were able to see the data that was there before, wouldn't that be
it absolutely would be. Hence why most people who are hacker type guys like to use C and C++ because it lets you walk through memory. Yeah, if any of you have ever cheated at a video game with like a bot or something like that, when a game comes out with a new patch, a lot of times you have to wait for your bot to come up with their patch because what it does, like for instance, a good example, not that I have any experience with this, but World of Warcraft is a kind of a famous game for having bots. And Blizzard, company that makes it, Blizzard Activision, what they do is they put in hard-coded memory addresses in there for where the stuff lives as a security measure. And then when they update the game, they change those memory addresses. So all the bots break for a day or two until they go and figure out where those memory addresses are again. What do they do? Big old for loop that goes through all of memory looking like, well, okay, where did Blizzard put it this time? Where did they put it this time? And so on and so forth. But absolutely. Yeah. I mean, this is wild, wild west. We can walk through memory, no harm, no foul. At the very least, even with protected memory, we can read it. It might not let us write to it if it's in protected OS based memory or something like that. But yeah, we can read memory. When you get into the 450 class systems programming, you're going to look at systems calls at the operating system level for how do you read and write stuff between OS space, protected space, and user space. So there's some special tools that let you, bridge the gap between those. So kind of break through. But it requires the program run in a certain with certain privileges. But to your point, yes, it's dangerous. It is a security issue. But bottom line for us, without going too deep into this, is this data here is meaningless to us, right? Whatever data, it's just whatever was there. So whenever you have memory and you want to do something with it, you put what you want there. All right, so we've done that. And we've proven that I can define my memory here. I can then pass it into another function, and I still have access to it when that function's done. I can then pass it into another function. I still have access to it when that function's done, because that memory right here only dies when main dies, because it was defined inside of main. Make sense? So if you fully understand that concept, then you know when it is safe to define arrays that way, rather than the cool kid malloc way. Because if we write this the malloc way, I'm just going to show you one thing to kind of complete the loop here. If I say int pointer AR is equal to the int pointer version of malloc 100 times size of int. Okay, I'm asking for enough memory to hold 100 of however big an integer is, which is 4 bytes. This is 400 bytes of memory. Give it to me as an int pointer, so I know how, when I take steps through it, how big the steps are, and store it there. You're going to see that this still works, but we technically have a little problem here. We have, how many of you have heard of something called a memory leak? What's a memory leak? Anybody know what it means? Go ahead.
Memory leak is when you forget to erase the memory that you just used instead of having the operating system do it.
Yep. So this program just ended, yet because I specifically, I'm the one who talked to the operating system. I asked the operating system to allocate me some memory. And because when this program ended, I never gave that memory back, technically, it's still reserved for me. So now that little chunk of memory that's sitting out there, unless the operating system has safeguards put into place to fix this, which most modern operating systems do, I have now reduced the actual usable amount of memory in my computer until the next time the computer is booted by, in this case, 400 bytes, because I never gave it back. Make sense? Yeah. Yeah. Oh, absolutely. Yeah. With older computers, right now, 400 bytes is nothing to us, right? But we can pretty, I mean, if I just put a giant number here, we can pretty quickly make this a problem, right? Right. But yeah, at home, if you make a mess, you should clean it up. Same thing's true here. So I'm pretty sure in C++ it's just delete. So when we're done using our memory, delete the memory, wipe it up, clean it up, give it back to the operating system. Make sense? Okay. And you'll see here that if we don't do that, it'll still run. We just didn't clean up our mess. And we've kind of left it to the operating system to deal with. And, hopefully it knows how to clean up after us. But at the very least, even if it does clean up after us, we've technically slowed down our operating system because we've given it an extra task that it shouldn't have been required to do. Because what does it have to do? It has to go through its 16 gigabytes of memory, whatever your computer has, and look for things that have been abandoned, orphaned memory, for it to say, hey, nobody's using this. That process ID is dead. Okay, the owner of it is usually a process ID, a unique number assigned to every running program. It notices that this program is no longer running, yet he owns memory. That's a problem. So it can then clean it up. But the fact that the operating system had to go through and search for that stuff is extra work that it shouldn't have to do, when we could have just been, a good boy and cleaned up our mess. Make sense? That's something that most modern programmers do not do, because most modern programmers don't learn with an older language like this. So they're not used to having to deal with implementing memory themselves and giving that memory back. Instead, they just become complacent and rely on things like Java that have automatic garbage collection. Java goes through and cleans up your memory for us. It's like you have a little maid following you around. Butler, go ahead. It won't zero it out. I doubt very much it would zero it out. An interesting question. I'm guessing it'll be the same stuff that was there before. Actually, but I won't be able to get to it. Guessing it's gonna tell me this. I don't own that memory. Nope, still there. Yeah, it doesn't zero it out. Wait, hold on. Let me not print it there.
So many numbers get replaced though.
No, I don't know if they're getting replaced. I think they were there before.
Yeah.
Yeah, no, I know what you mean. So why were those extra values there? It's possible.
They're the same numbers every time.
Well, yeah, but I mean, it's, so maybe, what were the, here, let me put this back in. Let's just see if it added to it or overwrote the first few. So I have the 54. So these guys, so this is 4, 16, 32. This is 32 bits worth of, no, this is 128 bits of data that could overwritten with stuff. Maybe it's marking it as not available, like it's no longer owned by something. I'm guessing this is something the operating system's doing, marking it as this is no longer available, but that's not how an operating system keeps track of who owns what memory. They have a table that they keep track of, like a database that says this process ID owns memory. Yeah, so I can give you a great explanation of why those numbers changed to that, but at the very least, the answer to your question is no, it didn't go and zero it out for most of it. Something is happening to those first 4 integers in terms of those memory spots, and it probably has something to do with what delete is doing. But you, at the very least, you can't rely on it afterwards. Once you've deleted this memory, you shouldn't try to use it again. It's no longer, you no longer own it. But to his point, you're still able to access that memory, which might be a security problem. As long as you have a memory address somewhere, you can go and read from it. All right, that makes some sense. So I would say the best programming practice would be to ask for memory this way, delete it when you're done. That's you as the programmer taking full responsibility over the memory that you're using, which then takes a little bit of the load off the operating system. Now, as computer users, though, we're saying, look, computers are really fast. I don't care if the computer has a little bit extra load, not my problem. And you might say, you know what? I am completely cool. Oh, I already have it in there. Let's just go. I'm fine with that. You could still delete that memory. I think you have permission to delete it. Yeah, it gives you a warning. It's basically saying this isn't yours to delete. It's run by the program. So you don't even get to clean up your mess officially. All right. Questions about that? All right, so now let's address the problem of this 100 bucket thing. So now we've filled it up with some numbers. We've seen, when arrays die and things like that. We're going to say, you know what? It's pretty bad programming practice to hard code the size of these arrays in here just because we happen to know. This fill array should be able to take something in and fill arrays of any size. This print array should be able to take this in and print arrays of any size. So what could we do? Well, we can take in 2 parameters. We can say this guy also takes in a size. And this guy also takes in a size. I need to update them up here. Just as a quick show thing here, I'm going to leave it like that for a second. We'll pass in the 100 here for the moment. Okay. See, that guy still works. And you're going to look at this and say, wait a minute, you didn't give a variable name here. C, C++, any programming language, it doesn't care what the names of your variables are. What's the purpose of these prototype functions? Why do these guys exist? Why do I have these one-liners up here and then I have their implementation later on? Is it just for fun? Why have I prototyped those functions? Which you don't have to do in new and more modern languages. C, or in Java, C#, you would not have to prototype your functions. You can just write them once. Why am I doing this here, though? What problem am I solving? But
That way, if you have a function below main, you call it main, it won't know what you're talking about. You have to get them in the right order, and you have two functions that call each other, it doesn't work.
Yep. So the idea here is that if main tries to call one of my functions that I haven't implemented till down here, it's never heard of it. Doesn't know about those functions yet. So what am I doing up here? You know, I'm giving it a sneak preview, sneak peek into what is to come. I don't have to have it implemented. I just have to give the compiler enough information to know that when it runs into something like this here, it knows that, oh, there will be something called filled array or fill array later on. Make sense? Which means that it doesn't actually need to know what these variable names are. It just has to know that I have a function called fill array that's going to require an int pointer and an int. I only need to add the parameter names down here. Why do I need to add the parameter names down here? Where I'm implementing it. Go ahead. I'm working with it. Yeah, when I start messing with it down here, I'm expecting two things to come as input. If I haven't given those guys names, it's not, I have no way of talking about them. I have no way of saying, oh, I want to fill up AR. There is no AR. Make sense? So we need the variable names down here in order for us to reference them in the body of the function. But up above, we only need to tell C and C++ that it's going to take in an int pointer and it's going to take in an int. Doesn't matter what you call them inside because I'm not implementing it right now. Having said that, it's not wrong to just put your parameter names there. Just wanted to show you that it's not required. Okay. I would always write it like this. Part of it is that I very commonly just copy this and paste it down below for my implementation to avoid spelling errors and things like that. So nothing's wrong with putting your parameter names there. You're just not using them at the moment. So it's a little bit of a waste of time other than maybe just a sanity check for you. Okay. So I can pass in the size and now I have the size. So if I want to change this to be 1,000, now it still works for that size array. You know, maybe I decide, okay, well, I'm going to have an int size is equal to 1,000. And then I can just use a variable in all these places for passing it in. So now if I want to change it to 10,000, I just need to change it in that one place. And now I have my functions work on arrays of size 10,000. If I want it to be size 3, I can change it to size 3. Make some sense? All right. So we're we're heading towards something that's a little bit more palatable. Like, okay, I need to, if I want this function fill array to be able to take a memory address and fill it up with some stuff, I also need to provide it with information about how big that memory address is. But let's say that I only want fill array to take in a single parameter, not two parameters. We're just arbitrarily making rules here, right? Okay, I'm just saying, well, you're not allowed to pass in two parameters just because. So now you have to get it all squeezed into one parameter. What kind of variable type do we know about that can allow us to hold more than one value inside of a single variable type? Struct. Okay, so I can invent a struct, right? So similar to what we did for player there, I can say I'm going to have a struct called int array. Perfect, thank you. All right, and I can say that this guy is going to hold an int pointer, and he's also going to hold a int size. It's going to hold those two pieces of information. All right. So I kind of packaged it up, right? So now down here, I can go ahead and say, okay, well, here's my int array. There's my size. I'm going to go ahead and say a struct int array. Call this guy IA struct, int array struct. We'll say IA struct dot AR is equal to AR. IA struct dot size is equal to size. And really, I could have done this. I would have said int pointer malloc size times size of int, like that. And then I wouldn't have had that there. So I'll keep a variable for the size. Go ahead and define a variable of type struct. Define my memory for AR. So I went and allocated memory. Because once I've done this, I've lost my opportunity to use that quick shortcut, the syntactic sugar for generating arrays. Once I've said I'm storing it as an int pointer, I no longer have the ability to generate it that way. So I'll use malloc. And then I just set the size. So now I have a single package of type int array struct. So now for fill array, I can say that this guy is going to take in a struct int array like that. And actually, hold on, I need to give it a variable name. Call that my struct. So its type is struct int array. The name of the variable is my struct. So I'll tell it's going to take in a struct int array, my struct, and then inside here we'll have my struct dot size, and we'll have my struct dot AR. That makes sense? And we'll do something similar for print array. Update print array up here. So now for both of these guys, we're going to pass in our IA struct. What are we mad about? And automatic size times. Oh, it's not a capital O. All right. So there's me packaging it together inside of a single variable. Not that it's substantially easier to read or anything. But I can do it. Okay. So now let's go and look at how we could maybe pull off sorting. And then we're going to talk about where we start hitting a walls with structs, which then takes us to objects. Okay. So your job was to sort the array from smallest to largest, right? And I said somehow. You could have gone out and found one of the sorting algorithms like insertion sort or something like that. But I suggested you kind of, hack at it and figure out a way of doing it. All right. So now I happen to know that all my values in there are greater than 100 or smaller than 100 rather, right? That makes sense? Okay. So one thing I can do is with that knowledge, again, just hacking at it to get this done reasonably quick. With that knowledge, I can say, well, I'm going to go through and I'm going to find the very smallest value in there that's not greater than 100. And when I find the smallest value, I'll go ahead and keep it. I'll store it someplace else. And then I will overwrite it with a value that's bigger than 100, marking it as already found. Make sense? Because it's a value greater than 100. If you didn't necessarily do that, you could say, well, maybe you say I'm only storing positive numbers in there. So then you can mark any of them with a -1. Or if you say, look, it's in the range of all integers, negative 2.1 billion to positive 2.1 billion. Well, then you can cross your fingers and go through and say, okay, let's go and look for the very largest value that I see in there. And now I know I can mark all the other ones with a value one larger than that, and that's allowed. That's me marking it as have already been picked. Make some sense? All right, because we have to have some way of going through and finding what is the smallest value in the array. What's the next smallest value in the array? What's the next smallest value in the array? So on and so forth. All right, if we're just going pure brute force at this. Most of our sorting algorithms don't require you to do that. Most of our sorting algorithms, for instance, insertion sort, it starts off at bucket 1 and it takes each value and tries to move it as far up in the array as it possibly can. And when you've gone through all the elements, then what you're stuck with is an array with the things in order because you've taken every value and you've moved it as close to the front as you possibly can, leaving the larger values at the end and the smaller values at the beginning. Okay, so that's one of our sorting algorithms. All right. So if we want to just see that real quick, I can go ahead and we'll just create a void sort. I'm going to call it insertion sort. All right, and this guy will take my struct int array, my struct. All right, so I'm going to go ahead and I'm going to have my loop start at bucket 1 and go to the end. So I'm going to say for int start pause is equal to 1. Start pause is less than my struct dot size start pause plus plus. So this is a loop that will take my number from 1 to 2 to 3 to 4 all the way up to the last legal bucket of it. Now, inside of here, though, I want to take whatever value I'm currently looking at, and I want to move it. I want to swap it with the guy before it over and over again until I've moved him as far up as I can. All right. So I have to remember where I'm currently starting with. So I'll say something like int cur pos is equal to start pos. Now, as long as I can do a swap. So while cur pos is greater than 0, because once I get to the very first bucket, once I've moved my number to bucket 0, I have nothing before it to compare to, right? So as long as I possibly have a predecessor that might be smaller, that might be larger than me, that I need to switch places in line with, I'm going to check. So while cur pos is greater than 0, and my struct .ar at bucket start pos, I'm sorry, cur pos, should come before my struct .ar at bucket cur pos -1. So as long as I'm not at the very beginning and the current guy I'm looking at is smaller than the previous guy, do a swap. And temp is equal to my struct .ar cur pos, my struct .ar at bucket cur pos is equal to my struct .ar at bucket cur pos -1. So preserve the value at position cur pos, overwrite the value at position cur pos with the guy right before him, then overwrite the guy before him with my preserved value. And do that over and over and over and over again, and then make sure that you do have cur pos follow. Sometimes I call this the follower, and it's like the follower. And he's like, he just follows him up the list. Okay. So as long as I'm not at the beginning and the guy I'm currently looking at is smaller than the guy before him, swap those two in line. And then follow the guy I just swapped closer to the front. Keep doing that over and over and over again until either I've gotten to the beginning of the array or these two guys shouldn't switch places. And as soon as I find the first one that can't switch place, then I've gone as far as I can right now with this dude. Go ahead. Trying to show so if I have 3 numbers and I have this number here and this number here, and I say, should this guy switch places with this guy? I need something that's always going to point at him. So that's cur pos. So if he changes position in the array, I need to make him now go there. He follows this guy through the array. So I always know where's the current guy I'm trying to get to cut to the front of the line. So I point at this guy here, and if he's the current guy, I'm trying to move him as far up in the line as possible. As he moves, I need to follow him so I can ask about him again. Because I'm not remembering him, I'm remembering where he is. Bucket 7, bucket 6, bucket 5, so on and so forth. Yeah, so I'm making sure that I can always ask this question about the element at bucket cur pos. And in order to do that, cur pos has to follow him as he moves up the list. Cur pos starts off at whatever my current starting pos is. So the first time through, I'm looking at bucket 1, comparing it to bucket 0. My second time through the outer loop, I'm looking at bucket 2, comparing it to bucket 1 and potentially bucket 0. The next time through, I'm starting at bucket 3, comparing them to bucket 2, potentially bucket 1, potentially bucket 0. So I'm going to each starting point and moving that guy as far forward as I can until, look, you belong, as far as I'm concerned right now, you're where you belong. I can't have you swap positions with this guy because he's smaller than you. I'm trying to put these in order from smallest to largest, and you're bigger than he is, so you don't belong earlier in the line. Make sense? All right, and I'll do that for every single one of the values. That's it for insertion sort. So now what I can do is I can say fill array, print array. I can call insertion sort on this guy. I'll pass it my AI struct, which seems very inconvenient at the moment. Then I'll call print array, passing it my AI struct. AI IA struct. And I should have a sorted dude there, I think, is my second one. So there's the original, and then there's the sorted version of that dude. And the name of that sorting algorithm is called insertion sort. It's one of our most inefficient sorting algorithms. And even if it's not, even if like, oh, I didn't do it that way, I bet you at the end of the day, you did it something close to that way, even if you did something where I did my thing I said at the beginning, I did a hard coded type thing where I said, look, I'm going to go through, I'm going to find my biggest value that's in there, which I know I don't have any values in here greater than 100. So I can just assume I can mark any position I've already placed with a 101 because that doesn't exist in my data set right now. So I can go through, find the smallest value, place it at the beginning of a new array, then mark that position as a 101. And I'm ignoring anytime I see a 101 because that's a already placed value. So go through and keep finding the next smallest value, placing it in a copy array, placing it. Now I've placed them all in order and then copy all those guys back over to the original. And now I have a sorted array as well. Pretty brute force. Nothing good about it, but it'll feel like it runs fast. What's up?
I was just understanding.
Oh. All right, but insertion sort is not considered to be a great sorting algorithm. But notice that for, I'm guessing most of you, as you see this, even though I said it out loud, you're going to want to walk through that by hand. I'm not going to be testing you over insertion sort or anything. I was just showing this to you really quick. You won't really understand what's going on here more directly until you kind of walk through it by hand. I kind of went through it quick just to kind of knock it out there. But at the very least, you can see that this isn't an overly complex sorting algorithm. But the second we get a loop inside of a loop, things are going to get a little intimidating, right? So if you're looking at this, you're saying, okay, that's kind of magic. It's not, but you're not necessarily supposed to just look at that and say, oh, I know exactly how that works. It's the magic is hidden inside of the swaps right here. Go ahead. No, I can sell it. Let's go. Which is better? Do you like the copy of all the code onto Slack, or do you like me to give you the link? The link is better. So I got to save it and then share. And now I have a current, that's a current snapshot of it, right? All right. Can you attach this to like a Venmo paywall? With structs. Let's go with that. All right. All right. Questions about that dude? And again, I'm not testing you over insertion sort, at least not yet. We might look at this more closely in the 250 class. But for right now, it's like, hey, sometimes it might make sense to put crap in order. This is one of the ways we can do it. Go ahead. Oh. All right. So now we've created, even though it seems very, I don't know, using structs, it's nice that you can stuff a whole bunch of values inside of a single variable, but I don't know, it's not that all that friendly to use, right? Okay. Also keep in mind here that we were actually passing this in by value. By default, structs are passed by value. Not really a problem because what does my struct contain? So, I think about it like I have a lunch pail, a lunch box. And inside that lunch box, I've thrown the memory address of an integer, an integer array, but it's a memory address. And I've also thrown in an int. So I've given it, so that struct, the weight of the lunchbox is however much a memory address of an int weighs, which is in this operating system is probably 8 bytes, 64 bits, plus however heavy an int is. How heavy is an int? 4 bytes. Okay, so really the weight of the lunchbox as I'm using it here is 12 bytes heavy. Make sense? 12 bytes heavy. And I'm passing the entire lunchbox to my arrays here, to my functions here. Now, if I say I'm going to pass a struct int array pointer instead, now instead of passing something that weighs 12 bytes, I'm passing something that weighs presumably 8 bytes, the size of a memory address. And through that memory address, I can get to my 8 bytes and my 4 bytes. We're not talking about a major difference here. It's the difference between, handing it the memory address where you can find my lunchbox, and that memory address weighs 8 bytes, 64 bits, or handing you the actual lunchbox, which weighs however big an int array is, 8 bytes plus, a memory address of an 8 bytes plus 4 bytes for an int, the size. So 12 bytes. 8 is still less than 12. It's still better to pass the pointer, but you're seeing here that you do get that choice. You're empowered to have that choice as a programmer. Now, what ability, if I did, let's assume, like we just described, that the difference between something that weighs 12 bytes and 8 bytes is not gigantic. Probably not the end of the world. Maybe if we go back a bunch of time in the early days of computing when memory was really expensive, maybe it is a bigger deal. All right. But, we can say now that, hey, look, that's not the greatest reason in the world to start screwing around with pointers here if I don't have to. Okay. Now, having said that, if I pass this struct in, I'm thinking, I don't know if they're plugged in or not. Are they? You can plug in the front if it'll reach the front wall. Teamwork. All right, so let's talk about, before I move on to classes, let's talk about the limitation now. If I'm passing a struct in by value, we're talking about pass by value versus pass by address. If I'm passing it, here is my struct as a value, what can't I do that I could do if I passed it in by address? Go ahead. Make changes to the original struct, right? Now, but I'm trying to trick you here, so be prepared, take a defensive stance. We saw, though, that when I passed in my struct here by value, I was able to change the array. We saw that when I passed in my struct here by value, I was able to change the array.
But the array was stored as a memory address.
The array was a pointer. So yeah, I'm giving it that lunchbox, the physical lunchbox. But inside that was a pointer to a memory address, and I was able to change that guy, just that point of it. So really, what can't I change in my struct that and have it have side effect? Couldn't change the memory address itself, so I can't kill off my, I can locally kill off the array. I can locally allocate new memory to that integer pointer. But then after this function ends, that would go back to the original. What else can I do? What's the other value in there? Go ahead. Yeah, I can't change the size. Again, I can locally change the size. So if the very first thing I did in here is I say, my struct dot size is equal to 13, I can do that. I probably just broke the world for what I'm trying to accomplish here, but I'm allowed to do that. And for the rest of this function, the size will be 13. But as soon as this function's over, it'll revert back to whatever the value that was passed in is, because I'm modifying a copy of this struct. As opposed to if I passed in a struct into array pointer, I would then say that guy dot size equals 13, and now I've changed the original. That has side effect. Go ahead. As which part called dereferencing? This? Yeah, this would be dereferencing the memory address. So this is a memory address. Give me the value at that memory address would be dereferencing the memory address.
So it's like, okay, why does that make a difference? You know, I mean, you really only, you changed two things. All you did was you added asterisk and the parameter in asterisk, to dereference everything. And it's like the function's still eventually going to end. So like what actually happens when you dereference? Like
well, the difference is what was passed in here. So if we leave it like this and up in insertion sort, when I call insertion sort here, I would pass in the address of that guy.
there's just something about like something.
No, I mean, the type of parameter has changed. Well, I mean, it makes a difference it's a reasonable question. It depends on what you're trying to accomplish. In our case here, it doesn't give us any benefit, right? In our case here, it was like, look, I'm not going to change the size. And even if I did, I don't need anybody externally to have access to my new size, right? I am going to change the contents of the array, but this guy already contains a pointer to an array. So I already have the ability to change that place in memory. Okay. So I don't gain anything in terms of what I'm trying to accomplish here by passing in a pointer instead of an address, other than I'm handing in something a little bit lighter weight. I probably used an example a couple of classes ago about, like when we were talking about pass by value versus pass by address, if you're having a party at your house, do you hand me the house and tell me to open the door at 8? Or do you give me the address where the house is and say, show up here at 8? You give the address because houses are heavy, right? And in an example like that, it makes a lot of sense because houses are very heavy relative to a little post-it note that has the address on it, right? Or a text message with the address on it. Okay. In an example like this, things are a lot closer, right? Our example was, I'm passing 12 bytes of data instead of 8 bytes of data. Is that the end of the world? That's not the difference between a house and an address, right? It's the difference between a full pizza and a 3/4 of a pizza or something like that. So there really isn't a generic answer to your question of who cares, but it's a reasonable question to ask, because don't just arbitrarily say, oh, I'm going to pass a pointer because that's better. It's not necessarily better. It's what are you trying to accomplish and what's going to allow you to accomplish it. The question would be here, pass in the pointer if you're going to make changes to this struct that you'd like to be felt externally, that you'd like other parts of the program to notice those changes. We call it having side effect. You'll pass in a pointer then. Alternatively, if the weight of the weight of the thing you're passing in is way heavier than an address to it, then you might say, you know what, I'm going to pass an address because passing the whole thing is memory inefficient. But I think if you're comparing 12 bytes to 8 bytes, it's not unreasonable for you to say, look, I don't want to have to say star that when I can just say that. Saves me just a little bit of typing at the cost of 4 bytes. Probably not the end of the world. Yeah, so definitely don't look at passing something by a pointer as better. It's what's the right tool for the job. We are empowered as programmers in C and C++ to decide what gets passed in by value and versus what gets passed in by address. We get to choose. In a language like Java, they make the choice for us. We don't have a syntax for pointers in Java. A lot of Java textbooks will say, well, pointers don't exist in Java. They do. You can get a memory address printed out in Java in less than a minute, very easily by defining an array and printing out the value of that array. Poof, memory address. They exist. That's what a pointer is. It's a variable that holds a memory address. The difference is in Java, we don't have a special syntax to make the decision of, am I passing this by address or am I passing this by value? Instead, Java makes the decision for us. It just says, oh, this is what is the smartest thing to do. Anything that is an object in Java, and let's just for the moment assume structs and objects are the same thing. This is kind of the, the step right before an object. In Java, anytime you're passing an object, you're passing it by address, because the address will weigh less than what's in the object, even if it's just marginally less. Like in our example here, yes, the 8-byte address did weigh less than the 12-byte full struct. In Java, they'll say, that's enough. We're going to go ahead and pass it by address. So every single object in Java is passed by address. And there's no special syntax for it because Java doesn't have the syntax for the asterisks and the ampersand things. C# does have that syntax, but only if you put it inside of what's called an unsafe code block. Okay, which takes us back to what he talked about earlier is, oh, isn't that a security problem? The second you start walking memory, we're going to say that that's kind of a less than safe thing to do. It's kind of like this is a hard hat only area. So you have to put it inside of an unsafe block, and then you can use pointer syntax inside there. But you're kind of taking responsibility yourself for saying, look, I either know what I'm doing, or I purposely am doing bad things. All right. Whereas Java doesn't even give you that option. In Java, there is not a syntax for dealing with pointers, which 99% of the time helps you, makes life easier. You don't have to do these dereferencing things, stuff like that. It works the way it's supposed to work because that's the way it makes sense to work. So you don't have to use special syntaxes all over the place to meet your current needs. But every now and then, I can't come up with a great example at the exact moment, but every now and then you want to do something a little bit funky, or maybe you want something passed by value. Maybe we have that scenario that in real life, you actually do want to hand them the house and have them open the door at 8 p.m. for some strange reason. That's going to make sense in the problem you're solving. In C and C++, well, C doesn't have objects, but in C++, you can do that. In Java, you can't. In Java, you are passing the address to an object every single time. C++, you just should pass the address to an object basically every single time, unless for some reason you are just really motivated to pass the house, or you're trying to write a program just incredibly memory inefficient. But you can do that by just putting an infinite loop with a bunch of mallocs in it and keep allocating, a million bytes of memory in a row. And pretty quickly it's going to scream at you and say, hey, look, you got a lot of memory in this computer, but a million bytes in a row is a decent amount of memory. And you've just asked for it a billion times. You're out of memory, dude. So take a hike. Which is why modern operating systems, they give you a kind of a bubble that your program's living in. So you can kill off your memory space for your program. You run out of stack space or heap space, but you don't affect the rest of the world. Kind of screams at you, says, look, something went south here. I don't think this does what you think it's doing. And if it does, don't do that. And then you can go in, like in Java, you can go in and modify the runtime to give you more heap space or something like that to allow you to do things reclaim more memory that it thinks is reasonable for your program. But you have to jump through a couple of hoops to kind of really reassure the operating system that, yeah, I'm doing this for a reasonable reason. A lot of times you'll see that with like scientific simulations and stuff like that, things that by nature do take up a lot of memory. And it's not because you're doing bad things. It's because the thing you're doing is just uses memory. Yeah. So, all right. Questions about that stuff? So.
Okay, just a question about the code mechanism when you have the my struct that they are but then you have the -1. Wouldn't that just always come up as false since you have -1 and it's always going to be less than?
Are you talking about this line here?
Yeah.
Well, no, I mean, this is the location. So this is a part of the array. So let's just say Kerpos is 5.
Okay, sorry, I understand.
Yeah.
Sorry, I just realized.
Yeah.
That
Is the value at bucket 5 less than the value at bucket 4?
Okay, sorry.
That's what it's asking.
But
And actually, but in the moment, let me add one thing since we're almost done with class anyways. But I'm only going to ever ask this question if this guy is already true, because we're dealing with an and. And in order for an and to be true, both sides need to be true. And C++ is smart enough to say, look, if you have a false right here, false and anything will be false. So I'm not going to check this other part. And that's an important piece here, because the reason why we're saying as long as Kerpos is greater than 0, I don't want to check bucket 0 to bucket -1. If it is 0, comparing bucket 0 to bucket -1 is going to be bad news bears. There is no bucket -1. All right. So by me saying, hey, look, as long as it's greater than 0 currently, as long as it's at least 1, and this is true, let's do the swap. But I won't ask the second half if I am at a 0. If I'm at 0, I won't check 0 to -1. And that's an important piece there, because otherwise you're possibly throwing an error into your code by saying, look, I might be talking about a negative bucket in my array, bucket -1. And that's not a place. There is no bucket -1. Why would I ever ask that question? We're only asking that question if Kerpos is at least a 1. And Kerpos is a moving target here, because as we're doing our swaps, Kerpos is getting smaller and smaller and smaller. So once we finally get to bucket 0, then I can say, look, I'm done swapping. We've done really great with this guy, right? We've taken him from wherever he started and we've moved him all the way to the beginning. But now we got to stop. No more swaps. I'm not going to compare him to the empty void after him. Go ahead. Well, because Kerpos all that is a position. So we have my array here, and I started off at, let's say, a bucket 3. If bucket 3 swaps to bucket 2, Kerpos is now just going to move, is going to go from 3 to 2. It's not the value that's there, it's where that value is. So he's constantly pointing at the dude he's interested in as he moves through the line. Yeah. Correct. Yeah, because what I'm doing right here is swapping. I'm preserving the current value, overwriting it, putting the old value into the other place, and then I'm following the dude I just swapped. Yeah, that's the ninja move we're making in here. We're doing a swap, and then we're updating Kerpos because now he's moved a little closer in line. All right. All right. Other questions on this? So we're going to come back. Oh, go ahead.
I realized I was trying to compare the last side of my array to +1 in my array with plucking off the end with both network.
Yep, right. And like I said, I'm not going to be testing you over insertion sort. I'd encourage you to go and walk through this by hand, because it's a good algorithm, and it's easy enough that any of you can understand it, but it's complex enough that you can't just glance at it and say, oh, I understand exactly how that's working. Keep in mind, I've written this a few times. So, I've done this a bunch of times. So this isn't just I pulled it out of the magical void. We're going to come back next time, and we're going to start talking about objects. And I'm going to start off class by asking you, what can't structs do? Structs can hold more than one value, but what's the thing they can't pull off that we might want them to pull off? And this is where programming starts getting very powerful, when we move to the object-oriented side of programming, and you're going to see what that means by object-oriented languages. All right, I'll see everybody on Thursday. I think do we have a tech talk this Thursday? Yeah. Oh, and for those of you who couldn't come to this last tech talk, if you would do me a favor and just turn in the Dropbox from the tech talk last week, just say I couldn't make it, whatever. I'll give you full credit because we canceled on you. But just give me something to grade and you get a free 100% in the homework assignment.
Okay.
Yeah, just give me a note saying I couldn't make it, but it was rescheduled on me. Just give me something I can just give you a full credit for. So you view it as extra credit. All right.
Oh, the picture thing, because I know like with the assignment things, they didn't get the date for the one that was canceled. Should we just put the pictures? Should we just submit it for the one that was canceled?
That's fine too. Yeah, I'm gonna literally give everybody full credit for it.
Okay.
Yeah, and there was a couple of people who wrote the paper anyways, so I'm gonna work with them to give them, because I wouldn't have made them do that because we canceled on you, which is, that's not your fault.
Yeah.